I'm going to go through the tutorial sheet. Well, I'm going to take you through the tutorial sheet. So let me show you where it is. Well, you might have seen it already. So the tutorial sheet is this one here. So I'll click here. So this is what you see. All right. So this is mainly this tutorial sheet is to do with distributions. So as usual, I will take you line by line, and also at the very end there are five exercises. I will try to do as many of them as I can, depending on the time. Okay, guys. All right. So let's go to page one of the tutorial sheet. All right. If you look at this table here, these are some of the discrete distributions you've seen, and these are some of the continuous distributions you have seen, right? And in R, for every distribution, there's a corresponding abbreviation. So for example, the binomial, the abbreviation is BINOM. For Poisson, it is POIS. For geometric, it is GEOM, and so on. And for uniform, which is a continuous distribution, the abbreviation is UNIF. For normal, the abbreviation is NORM. Exponential is EXP, and so on. Right? Okay, now what I'm going to tell you is about this table here, the bottom of page one. Now, for every distribution, you can use one of these commands. Like, for example, you should say D followed by the name of the distribution. That will compute the density of the distribution, right? Or the density values, either the PDF or the PMF, right? And if you say P followed by name, that will compute the CDF, or the probabilities associated with the distribution, right? And if you say Q followed by the name of the distribution, then it will compute the quantiles associated with the distribution. And finally, if you say R followed by the name, that will generate random numbers from the distribution. All right, so it's D, P, Q, R. It's not difficult to remember. All right, so for example, if you take the normal distribution, which is the most popular continuous distribution, D norm will compute the density of the normal. P norm will compute the probabilities associated with the normal. And Q norm will compute the quantiles of the normal. And finally, R norm will generate random numbers from a normal distribution. All right. So these four things, D, P, Q, R, apply to any distribution, right? I mean, in your lifetime, you will come across many distributions, but all of them are probably implemented in R. So R is a very useful package to learn, because it can compute pretty much any distribution that you will encounter, right? The density, the probabilities, or the quantiles, or the random numbers, right? All right, now so that's the first page. All right, now let me start with the second page now. So to do that, I'm gonna, as usual, if you have questions, use the chat room. So I'm gonna open R now. So you click on the start menu, and then you go to R, and then you choose the 64 version, and this is what you will get, right? So I'm going to take you through line by line now. The first thing I'm going to show you is how to draw the probability mass function of the binomial distribution. So I'm defining a sequence of numbers 0 to 50, and I'm going to compute the PMF of the binomial at X. Remember, binomial has two parameters. The size parameter, let me take it to be 50. And the probability parameter, let me take it to be 0.6. right? Then if you say plot x comma y, this is what you will get. So what I have drawn here, guys, is the PMF of the binomial with parameters 50 and 0.6. Now, if you like, you can join the points together. To do that, you say type equal to L. L stands for line, and this is what you will get. Don't confuse L with 1. I think some of you did. L is L, this is L, not 1. Okay? All right. All right, now next thing is suppose you have a variable x that is binomial with parameters say 50 and 0.6, right? And suppose you want to find the probability that x is say 35, right? To do this in R, you just use the command dbinom at 35 with size parameter equal to 50 and the probability parameter equal to 0.6. So the probability x equal to 35 is 0.415, etc. Right? Please, if you have questions, please feel free to use the chat room. Okay. Now, suppose you want to find the probability that x is less than or equal to 25. To do this, you will use the pbinom command. The P stands for probability, right? Probability at x less than or equal to 25. So you need to change this to 25. So this is what you will get. This is the probability that x is less than or equal to 25. Okay, now suppose you want to find the probability that x is between 20 and 30, right? Now remember, binomial is a discrete distribution, so it can only take integer values. All right, so you can write this probability as the difference of the following probabilities. Do you see what I have done? If you want all the numbers between 20 and 30, you should take all the numbers that are less than or equal to 30 and subtract all the numbers that are less than or equal to 19, right? And the first probability on the right-hand side, you can compute it as this, right? And the second probability on the right-hand side, you can compute it as, excuse me, as this. All right, so the answer is 0.552, etc. So that's the probability that x is between 20 and 30. Now, suppose you want to find the quantiles of a binomial. So you start with Q binom. Suppose you want to find, say, the median, right? So the median of a binomial with these parameters is, oh, sorry, is 30, right? Okay. And the first quartile, which is probability 0.25, is 28. The third quartile, which is probability 0.75, is 32, and so on, right? And finally, let me show you how to generate random numbers. To generate random numbers from a binomial, you will use the rbinom command. And suppose you want to generate 5 random numbers from a binomial with parameters 50 and 0.6, and this is what you will get. So these 5 numbers come from a binomial distribution with parameters 50 and 0.6. So if you repeat it over and over again, you will get different numbers because they are random. So every time you repeat a random experiment, you get different outcomes, right? I mean, that's the purpose of randomness, right? Okay. Okay, guys, any questions? Any questions so far? Please feel free to ask me any questions, guys. Are you okay, guys, so far? Talk to me, guys, please. You okay? Okay, thank you. You have a question. All right. So what's that? I have a question about R binom. What is that? Yeah, R binom, as I mentioned, my friend, is a command for generating random numbers from a distribution. So in this case, you're generating random numbers from a binomial with parameters 50 and 0.6. And the sample size that you're generating is 5. It could be any other, it doesn't need to be 5. It could be, say, for example, 10, or it could be 100. Example sheet 7. What do you mean example sheet 7? I don't understand your question, sir. Where is example sheet 7? Oh yeah. Okay. In that case, oh yeah. I see what you're saying. Yeah. So you should say 8 with size equal to 1 and probability 0.6. This is what you will get. Yeah, you're right. So here, remember, a binomial distribution with size equal to 1 is a Bernoulli distribution. Remember, binomial, when the size parameter is 1, is Bernoulli. So the possible outcomes can either be 0 or 1, right? So that's why you see when you do this, you're getting the outcomes can either be 0 or 1, right? Okay, you follow me, guys, or not? Size, yeah, the size is the. I'm sure all of you know the size in the binomial is the I mean, in my notes, I used M to denote the size. So if you look back, uh, if you look back on the, excuse me, if you look back in the my notes on the binomial, you will see I used the notation M to denote the size. So so the outcomes must be less than or equal to the size. So in this case, the size is 1, so the outcomes can either be 0 or 1, right? In the case over here, the size is 50. So the outcomes must be less than or equal to 50. I thought you did binomial in probability 1 last year. I mean, I thought you, anyway, I hope this makes sense to you, sir. Right? Okay, all right. Let me move on to the next page. If you guys are, do you guys have any questions and any more questions, guys? On the binomial? No? All right. So let me move on to page 3, where we talk about the normal distribution. Remember, the normal is the most popular continuous distribution. So if you type d norm at 0, for example, it will give you the density of the normal variable with mean equal to 0 and standard deviation is 1. So it should, so okay, R assume a standard normal if parameters are not specified. Right? So if you don't specify the parameters for d norm, then R will assume that the distribution that you're considering is the standard normal, right? Okay. All right, guys. Okay. So, but if you do specify the parameters, like for instance, if you say mean, remember there are 2 parameters for the normal, the mean parameter and the standard deviation parameter. So if you specify them, sorry, what did I do? Yes, spelling. Yes, spelling is wrong. This is what you would get. This value here is the density of the normal at 0 when the mean is 4 and the standard deviation is 10, right? Okay, now next let me show you how to draw a picture of a density of a normal, right? So let's define x to be minus 26 to 34 in steps of 0.1 and y to be the density of the normal at x, say with mean equal to 4, standard deviation is 10. Now, if you say plot x comma y, this is what you will get. So this, I'm sure you've seen this before. This is the density of a normal distribution with mean equal to 4 and standard deviation equal to 10. If you like, you can use the L for line. Now you see that the points are joined together by a line, right? Okay, the next thing is suppose you want to find the probability that x is less than or equal to 4 when x is normal with parameters 4 and 10 squared. 10 squared is the variance. Right? What you need to do this, okay, to do this in R, you will say P norm at 4 with the mean equal to 4 and the standard deviation equal to 10. All right, so it's 0.5. Now you can also use multiple arguments for the first argument. So if you say 4, 8, 12, you get 3 different numbers. The first number here is the probability that x is less than or equal to 4. And this is the probability that x is less than or equal to 8. And this is the probability that x is less than or equal to 12, right? Okay, when x is normal with parameters 4 and 10 squared, right? Okay. Now the next thing is about quantiles. Now, if you want to compute the quantiles of a normal, you will use qnorm command. So if you say qnorm at 0.975, this is the quantile of a standard normal with probability 0.975. Now, if you want it for a different normal, say with mean equal to 4 and standard deviation 10, this is what you will get. And if you want the probability to be 0.5, that's the median. That's the median of the normal with mean 4 and standard deviation 10. And this is the first quartile, and this is the third quartile, right? Okay. All right, next I'm going to show you how to generate random numbers from a normal distribution. So suppose you want to generate 5 random numbers from a normal with parameters 4 and 10. And this is what you will get. And once again, every time you type this, you will get different numbers because they are random, right? Okay. Any questions so far, guys? So that's all on normal, guys. Any questions you want to ask on normal, guys? Please let me know. Are you okay so far or no? Hello, guys. Talk to me, guys. Okay. All right. Thank you. All right. The next thing I'm going to show you is how to draw a histogram and how to superimpose on the same plot the density of a distribution or density of more than one distribution, right? So that's what I'm going to show you. It's on page 4 of your tutorial sheet. So the first thing I'm going to do is I'm going to simulate data from a gamma distribution. You might have done this in probability 1 of size 100 with parameters 200. And remember, the gamma distribution has 2 parameters, the shape and the scale parameter, right? So here I'm taking the shape to be 200 and the scale to be 2. The next thing I'm going to do is I'm going to do a histogram of the simulated data, and this is what you will get, right? Okay, right. Now let me take the y, as you can see, if you look at the x-axis, if you look at the x-axis, it goes from 300 to about 400 and something, or maybe 500. So let me define the x-axis. So x-lim, I don't know whether you know what x-lim is. Let me explain. X-lim is basically the limits of the x-axis. So the 300 corresponds to the lower limit of the x-axis, and the 500 corresponds to the upper limit of the x-axis. So that controls the how the limits, the lower and the upper limits of the x-axis. Similarly, you can define the y-lim too. Y-lim will control the lower and upper limits of the y-axis, right? If you want. All right, now what I'm gonna do now is I'm gonna plot on top of this histogram the density of the gamma that I simulated from, right? So for that, let me first define a sequence from 300 to 500, say in steps of 1, and let me define y to be d gamma, or the density of the gamma at x, with shape equal to 200 and scale equal to 2. Now, if you type lines x comma y with LTY, by the way, LTY stands for line type. Line type can take numeric values like 1, 2, 3, etc. Right? So line type 1 means it's a continuous line, as you was. Oh, sorry. What did I do? I think I made a mess up. Oh, I know what I did. Sorry. Okay, I think this should have been a sequence, not C. It should be a sequence, then Y, and then lines. All right. You see now. You see what I have done. So I have done the histogram. I've done the histogram, and on top of the histogram, I have drawn the density of a gamma distribution that I simulated the data from. So as you would expect, the curve is a good match to the histogram because the curve is the density of the gamma distribution that we simulated the data from, right? So it must be a good match. All right, now the next thing I'm going to show you is I'm going to take y this time to be the density of a normal distribution, right, at x, right, with the mean parameter equal to the mean of the simulated data, and the standard deviation parameter equal to the standard deviation of the simulated data. Right now, you should plot on top of the same on the window, say this is what you will see. Right now, you see there are two curves. The curve in black is the density of the gamma, and the curve in red is the density of a normal distribution, where the mean parameter is the mean of the simulated data, and the standard deviation parameter is the standard deviation of the simulated data. As you can see, they are pretty close to each other. That is, the normal PDF and the gamma PDF, they are good match to, both of them are good match to the histogram, right? But this is only true for this particular data set. I mean, it may not be true in general. In general, the normal distribution may not be a good approximation to the histogram, but in this case it is. Now, to show you this, let me give you an example. Let me give you an example where the normal distribution is not a good fit to the histogram. I mean, this example that I'm going to give you is not in the tutorial sheet, so it's something that I made up myself, right? So let me take you through this. Now, what I'm going to do is I'm going to simulate 100 random numbers from an exponential distribution using REXP command. So these are the numbers I just simulated. Right now, I'm going to do a histogram of this with frequency equal to f, and this is what you will get. Now you see the limits of the x-axis are from 0 to about 5. So let me define x lim to be 0 to 5. All right, so this is what you see. Okay, Now, the next thing I'm going to do is I'm going to define x as a sequence from 0 to 5 in steps of 0.1, right? And then define y as the density of the exponential at x with the rate parameter equal to 1. Now, if you draw the lines, x, yeah, with line type equal to say 1, this is, now you see it's a good match. The exponential PDF is a good match to the histogram, as you can see, as you would expect, right? Because we simulated the data from an exponential. So the exponential PDF should be a good match to the histogram. Now, let me try to do what I did earlier, right? That is, define y as the density of the normal at x with the mean parameter equal to the mean of the simulated data and the standard deviation parameter equal to the standard deviation of the simulated data, right? And then I'm going to do line with a different color. Let's say red, okay? See, this is what you see. Now, the red curve is the density of a normal. The black curve is the density of an exponential. But this time, the normal density is not a good match to the histogram because of what I just said a minute ago, that it is the normal distribution always does not always give a good approximation to the data, right? As you can see in this picture, right? All right. Any questions, guys? Hello, guys. Are you okay with this or not? You fine? All right. So let me. So we are done with the tutorial. So I'm gonna go back to the tutorial sheet. This is the tutorial sheet, and there are 5 exercises. 1, 2, 3, 5. Okay. So I will start with exercise 1, which is this one. So I will show you how to do it. Right. So let's start with exercise number 1, right? So here we have a random variable that is binomial with parameters 100 and 0.3, right? The first part of the question is to find the probability that x equal to 33. Now this is easy, I'm sure you know. So the answer for this is d binom. Remember, sorry, d binom, right? At 33 with the size parameter equal to 100 and the probability parameter 0.3. So this is the probability that x is less equal to 33, right? All right, the next thing is to find the probability that x is between 28 and 34, right? All right, now this you can write, as I said before, this you can write as the difference of these probabilities. Right? Okay, guys, so this probability is the difference of these two probabilities. All right, the first probability on the right-hand side is P binom at 34. And the second probability on the right-hand side is P binom at 27. Okay, so this is the answer, right? Okay. Are you guys okay following me? Okay. Just if you have questions, please feel. All right, the next question is to find the probability that x is less than 38. Right, this is, now remember, binomial can only take integer values. So this is the same as the probability that x is less than or equal to 37. Right, now to find this, all you have to do is just put 37 here. That's what you get. So this is the answer for the probability that x is less than 38, right? Okay, are you okay so far? All right. So that's the first part of question exercise 1. The second part of exercise 1 is asking you to do a normal approximation, but this is stuff I did not cover in the course, so therefore I will skip it. All right. I will not, I mean, in the exam or anything, I will not ask you, I will not ask you a question on normal approximation. So you don't need to worry about part 2, right? All right, so next I'm going to go to exercise number 2. Exercise 2, we have a Poisson distribution, which is Poisson with parameter lambda equal to 10. The first thing we want to do is to plot the PMF of x over the range of values 0 to 25. So to do that, I need to define the sequence 0 to 25 in steps of 1. So this is what you get. Then you define y as the density of the Poisson at x with lambda equal to 10. And then you say plot x comma y, and this is what you get. All right, so what I have drawn here is the density of a Poisson with lambda equal to 10. If you like, you can use type equal to L, and you see a smooth version, right? Okay, guys. All right, the next part is to find the probability that x is less than 15. Right, to do this, the probability that x is less than 15, because x can only take integer values, is the same as this. All right, so to find this, you say P Poisson, right, at 14 with lambda equal to 10. So that's the probability. All right, the next, we want to find the probability that x is greater than or equal to 8, which you can write as 1 minus the probability, 1 minus the probability that x is less than or equal to 7. I remember. Okay, so it will be 1 minus P Poisson at 7 with lambda equal to 10. So that's the answer. And next, we want to find the probability that x is between 6 and 16, right? Now, this probability can be written as the difference of these two probabilities, all right? You follow me? Yeah. So to compute this, you say to compute this, first you compute the probability that x is less than or equal to 16, right? And then you compute the probability that x is less than or equal to 5, right? And this is what you will get, all right? All right, guys, so far, are you okay? All right, that's the first part of exercise 2. The second part is asking you to find the lower quartile, the median, and the upper quartile of the distribution. So remember, to find the quantile function, you use the qpoise command. The lower quartile corresponds to probability 0.25, all right? So with lambda 10, so the lower quartile is 8. The median corresponds to probability 0.5, so the median is 10. The upper quartile corresponds to probability 0.75, so it is 12. All right, so that's easy. All right, so this completes exercise number 2. You okay with this? Come on, guys, talk to me. Are you okay before I go to the next one? Any questions you guys have? Okay. Next one is exercise 3. All right, I'll try to do the 5-number summary later, guys. I mean, basically, a 5-number summary, remember, is basically the minimum. Minimum in this case, you can't talk about for a Poisson distribution, the minimum is 0, right? The maximum is infinity. So the 5-number summary will be the minimum, the lower quartile, the median, the upper quartile, and the maximum, right? All right. So we basically done it already, right? Except that the minimum and the maximum are 0 and infinity, respectively. Okay. All right. In this question, X is an exponential variable with parameter 0.2. The first part is asking you to draw a PDF over the range from 0 to 25. So let me define the range from 0 to 25 in steps of 0.1. And Y is the density of the exponential at X with parameter 0.2. And then you say plot X comma Y. This is what you get. So this is what I have drawn here is the density of an exponential distribution with parameter 0.2. If you like, you can use type equal to L. This is what you get. Okay. All right. Next, we want to find the probability that X is less than 12. Now, remember, for a continuous random variable, less than is the same as less than or equal to, and greater than is the same as greater than or equal to. So it doesn't make a difference. It's only when you have a discrete you have to be careful. But for continuous, you don't need to be careful. All right. So to find the probability that X is less than 12, you say P exponential. P stands for probability at 12 with parameter 0.2. So that's the one. Now to find the probability that X is greater than 3, you can write this as 1 minus the probability that X is less than or equal to 3. So this is 1 minus P exponential at 3 with parameter 0.2. And next, to find the probability that X is between 4 and 20, right? You can write this as the difference of these probabilities, right? Okay, so this will be P exponential at 20. It will compute the first, right? Minus P exponential at 4. So the answer is no, Pedro, I think you got, remember what I just said, X less than 12 is the same as X less than or equal to 12 because it's continuous. I mean, what I said a minute ago, man, is this, like for a continuous variable, this and this are equal, right? Yeah, less than or equal to does not make a difference. Right, so the probability X less than 12 is the same as X less than or equal to 12. And that's what I computed earlier, right? Okay. All right, the next question is, let me see where it is. So this is question 3 I'm doing right now. Part 2, all right, part 2 of question 3 is asking you for the 20th, 50th, and 80th percentiles. So to find the 20th percentile, you use the QF command with 0.2, parameter 0.2. So this is the 20th percentile. To find the 50th percentile, this is the 50th. To find the 80th percentile, is this one. Okay, guys, are you okay with this so far or no? So remember, percentiles is the same as quantiles, and quantiles is the same as quartiles. They all mean the same thing. Quantiles, percentiles, they all have the same meaning. So if you're looking for the 50th percentile, that's the same as the median, right? If you're looking for the 25th percentile, that's the same as the lower quartile or the first quartile. If you're looking for the 75th percentile, That's the same as the upper quartile or the third quartile. There are so many different names for one thing, the same thing, I mean, yeah, okay. All right, the next exercise is exercise number 4, right? Here, we are assuming that X is normally distributed with parameters, the mean parameter equal to 20 and the variance equal to 7 squared. So in other words, the standard deviation is 7, right? The first thing we want to do is to do the PDF, plot the PDF over the range from 0 to 40. So let's define the range from 0 to 40, say in steps of 1. Then the next thing you do is compute the density of the normal at X with the mean parameter equal to 20 and standard deviation 7. Then you plot X versus Y. I'm sure you've seen this before. This is a typical shape of a density of a normal distribution, right? If you join them up, if you join the points using lines, this is what you get, right? All right. All right, the next thing is we want to find the probability that X is less than 17. Again, remember, X is a continuous variable because it's normal is a continuous distribution. So the probability that X is less than 17 is the same as the probability that X is less than or equal to 17. So to compute this, you just say P norm, or probability of normal at 17 with mean equal to 20 and standard deviation 7. Okay, next we want to compute the probability that X is greater than 25. Now this you can write as 1 minus the probability that X is less than or equal to 25. All right, so it's 1 minus P norm at 25 with mean equal to 20, standard deviation 7. Right, next we want to find the probability that X is between 13 and 27. Right, this you can write as the probability that X is less than 27 minus the probability that X is less than or equal to 13. Okay. All right, so the first probability on the right-hand side can be written as this. And the second probability on the right-hand side can be written as this. So you see, you will get this. So the answer is 0.6826, etc. Right? You okay so far, guys? Yeah. Talk to me, guys. If you have questions, please. Yeah. All right. So that completes the first part of exercise 4. The second part is to find the percentiles at the 5th percentile, the 10th percentile, the 90th percentile, and the 95th percentile. So to find the percentiles, you use the command qnorm. So to find the 5th percentile, you put 0.05 with mean equal to 20, and standard deviation 7. So this is the 5th percentile. To find the 10th percentile, you put 0.1. To find the 90th percentile, you put this 0.9. To find the 95th percentile, you put 0.95. So these are the 4 percentiles corresponding to different probabilities, right? So that's part 2. Part 3 is suggesting a different way to compute the percentiles. I don't know if I taught you this in the class. If I did not, let me write this. If you have a variable X that is normally distributed with parameters, say mu and sigma squared, then the quantile function of X is the same as the following: mu plus sigma times the quantile function of standard normal. Maybe I didn't teach you this, but I don't know. Maybe you learned this in probability 1, I don't know. But this is a well-known result. This result, what I have written here, is pretty well-known. That if x is a normal variable with mean mu and variance sigma squared, then the quantile function of that variable x is the same as mu. Mu is the mean parameter plus sigma, which is a standard deviation parameter, times the quantile function of the standard normal, n01. Right now, let me illustrate this, right, for these four quantiles. For the first quantile, remember, for the first exercise, the mean is 20, the standard deviation is 7, right? So if I'm using this formula, right, I should write 20 plus 7 times q norm at 0.05. I get this, and this is exactly what I got earlier. Remember, these are the same, right? This and this are the same. So both approaches give the same answer as they should, right? Now, similarly, if you change this to 0.1, we get 11.029, and the same thing, 11.029. If you change this to 0.9, we get 28.970, 28.970. Now, if you change this to 0.95, you get 31.513, 31.513. So there are two approaches. So what I wanted to say is that there are two approaches for finding quantiles of a normal variable. One is to use the qnorm command with the given mean and the standard deviation. And the second approach is to use this formula here. Use this formula where mu is the mean and sigma is the standard deviation, right? Okay, guys, so this completes exercise 4. Are you okay? Any questions, please? Hello, guys, talk to me. Are you okay with this or no? Yeah, sure. Okay, thank you. All right, so there's one more exercise to do. I don't know if I have the time for that, but so if you go to, let me go to the tutorial sheet. So this is sheet. If I open this, so I've done the first 4 exercises, and exercise number 5 is this one. So basically it's asking you to do a histogram of each of these data sets, right? And on top of the histogram, plot the PDF of the normal. I mean, I have already done something similar to this. I mean, so it's just an exercise for you guys. If you want, I can do the first part. Okay, let me show you how to do the first part, and then I'll leave you to do the 2 remaining parts. All right, so let me go back to the website. So this is the simulated data set. So I will copy the URL and paste it here, right? So the header equal to, you know how to read a data set. I taught you this some time ago, right? So this is a read table. Let me call this sim data or sim dat, right? So this is the data that I just read, okay? The data that I'm interested in is this one, right? So what I'm gonna do is I'm gonna do a histogram of this. So I use hist with frequency equal to f, and this is what you will get. So this is the frequency of the data that I just read. As you can see, the x-axis goes from 6 to 16. So let me define x lim to be from 6 to 16, right? So that's what you see, right? Okay, the next thing is you define a sequence of x's to go from 6 to 16, say in steps of say 0.1, and then you define y to be the density of the normal at x with mean equal to 10 and standard deviation equal to 2. That's because the question says so. You should read the question, guys. I don't know whether, you should go back to the tutorial sheet. And if you read the question, part 1 of exercise 5, it says here that the data is simulated from a normal with mean equal to 10 and variance equal to 4. So the standard deviation is 2, right? All right, so that's what you get. And finally, you use the lines command, x, y, line type is 1. And this is what you see. So as you can see, the normal density is a good match to the histogram, right? Because that's what you would expect anyway, because the data was actually simulated from a normal with mean parameter 10 and standard deviation 2. All right, so this is the first part of exercise 5, and the 2 remaining parts are similar. So I hope you can do them by yourself. Anyway, I have already posted the solutions online. You should go to the YouTube channel or the university channel. You should be able to see the full solution to all 5 exercises, right? All right, and if you have further questions, please feel free to contact me 24/7 by emails, Skype, or Zoom, or phone. I gave you my home phone number, which is 0161 273 2941. All right, guys, any questions you want to know now? We are nearly done. We are done with the tutorial today. Are you okay, guys? Are you sure? Right, okay. Okay, have a great evening, guys. So wherever you are, I'll talk to you soon. Just and please, once again, please, any problems with the course, please feel free to contact me 24/7. Okay. All right. Have a good evening. All right.